Thank you for that introduction, Kevin. So unfortunately, this classroom is extremely wide, and I am going to be tied over here a bit because I will need to advance my slides. But very excited to be here today. So I run a lab at the information school called Large Lab or Language Accessibility Lab, where I primarily focus on, our group focuses on work around improving information access to people with different needs, and especially focused on this kind of high expertise information in the healthcare and science space. As part of my work, I kind of sit at the intersection of some disciplines, including natural language processing, health informatics, and increasingly more human-centered design work. And today, somewhat surprised, but also delighted to be sharing part of this work with the biostats community. So as part of my work, I spent a lot of time thinking about how to assess model performance, so how to evaluate language models for different tasks, how to evaluate whether they're serving their users. I guess for today's talk, I want to focus on parts of that. So what should we be measuring? How do we measure that, and how do we validate that the measures that we are applying are in fact well correlated to the underlying constructs that we're trying to measure? So I'll preface and say there's been a very large paradigmatic shift in the way that AI technologies are available to people. They're now pervasive across many aspects of people's lives, and we indeed also see that large language models and adjacent generative AI technologies are being applied to support information access needs across many medically relevant tasks. So for example, maybe healthcare consumers now go to their computers or go to their search engine and just type in a medical question, and usually they'll get a response back either from a chat interface or, for example, at the top of the search results page. These models are being used to support patient-provider communication. They're also being used in evidence finding, right? Finding and summarizing the latest and most relevant evidence, or to support scholars and practitioners in synthesizing the scholarly literature and conducting literature reviews. So I'm going to use this consumer health kind of question answering use case as an example to illustrate some of the evaluation challenges that we now face in this ongoing paradigm shift. So, right, I might, as a healthcare consumer, go to my search engine and plug in a question like this. So this is a question adapted from the KQA data set. This is a curated data set of health questions found on user-facing forums. And the data set also nicely provides these ground truth answers that were written by a panel of physicians. So we have some idea of what the correct answer is to this question. So maybe I go to my search engine, I plug in this question, and a couple weeks ago when I put this question in, since I took Fioricet about an hour ago, can I take ibuprofen? This is the response that I got. You should not take ibuprofen with Fioricet because Fioricet already contains acetaminophen and caffeine, and combining with an ibuprofen increases risk of liver damage and other risks. Okay, so now that you've read this question in this overview, who believes it is okay to take Fioricet with ibuprofen? Okay, who believes that it is not okay? Okay. All right. Well, in this example, at least, the suggestion given by the AI is actually incorrect. So Fioricet and ibuprofen are actually not contraindicated. If we click through, there's this citation at the end of this AI overview. If we click through to that citation, we land on this page at BuzzRx. I'm not sure how trustworthy this site is, but if we read the page carefully, we actually see that the site discusses a potential negative interaction with acetaminophen, but that NSAIDs like ibuprofen are okay. So actually what the AI generated in the overview doesn't agree with the source that it is citing here. And then if we look at the curated physician answer for this question, we also see that the physician answer says that NSAIDs like ibuprofen together with your set is safe. No known interactions. So in this case, we just have this somewhat incorrect answer, which misinterpreted evidence document and also differs from the physician answer. Okay, let's take a look at another example. So this one, same data set. Because I have fatty liver, can I safely take Imodium? In this case, the overview on Google replied with the following: no, you generally should not take Imodium if you have liver disease, including fatty liver, without strict doctor supervision. Okay. Who now thinks the answer to this question is no, like the AI overview? Okay. All right. Who thinks it's yes? Maybe I've primed you that maybe sometimes the models do funny things. I plugged the same question into ChatGPT 5.2, received the following answer. Yes, most people with fatty liver disease can safely take Imodium when used at standard doses. Okay, so there's some disagreement here. And actually, this is a trick question. This question was asked by a person in a health forum, but there's actually very little relevant evidence in this case that directly supports either of the conclusions that those two models came to. So neither contraindicated nor supported. So when I search for loperamide, which is the active ingredient in Imodium and fatty liver in PubMed, the search query returns only 2 results. And if you look at the titles of these articles, you also find that neither of these articles are particularly specific to our drug of interest, right? Neither of them really mention anything about loperamide. One is, So essentially, these articles are not very specific to our query of interest. And if we look at the physician answer in this case, what's going on? The answer provides a description of some background information about loperamide, this medication. And then it goes on to say that for patients with liver disease, it is recommended to use loperamide with caution and to consult a healthcare provider about possible alternatives. So this physician answer is actually a bit of a non-answer. It doesn't really say one way or another whether this action of taking this medication for someone with fatty liver is okay. So there's no direct recommendation. So this last example illustrates two claims I want to make. One is that models, and LLMs in particular, tend to answer poorly when there's epistemic mismatch. So when a question assumes knowledge that does not exist. For example, if there's no or low relevant scientific evidence related to the question, or to support a result, an answer for the question, excuse me. And then in these cases, the inaccuracies produced by these models may also be related to something like format-induced overconfidence. So because the question really strongly hints at a yes or no answer, it's a Boolean question, it suppresses this uncertainty in the model output. So these are some claims I want to make. And I'm going to try to back up some of these claims further with some study results. Okay, so these phenomenon, the two phenomena I've noted on the previous slide, epistemic mismatch and format-induced overconfidence, neither of these are very well studied in current evaluation. And because of the following: one is, most of the question answering benchmarks out there that we use to evaluate language models, they kind of have these implicit assumptions. They assume that the questions in those benchmarks are answerable. They assume that some evidence might exist for answering those questions and that systems should produce a response. And that's not always the case. I think one might make the case that in cases where there's high uncertainty, that maybe models shouldn't generate a response, or they should generate a response that essentially says that the question is not answerable. And then on top of that, when we think about this free-form generation setting where we're asking models to produce these long answers and rationales for these answers, we also lack dependable evaluation metrics to help us understand what's going on with these model outputs. This is not directly related, but I want to make the case that in these scenarios, our gold standard case is still to judge these answers through human or expert evaluation, right? We take a look at that physician answer, we look at what the model generated, we compare them and ask, are these saying the same thing? And this is not reasonable when we're trying to iterate on model development because human evaluation is too expensive and difficult to scale in that setting. So we still need some alternative strategy that we can apply that's quick and relatively inexpensive. On the other end of things, we can compute these automated metrics. But many automated metrics that are cheap to compute are also not well correlated with human judgments. And there's plenty of prior work that shows that to be the case. More recently, and maybe in work that you've all interacted with, there's an increasing use of LLM judges as evaluators, also sometimes called auto raters. And this introduction of LLMs as evaluator, I would say, creates this new meta-evaluation challenge. So as I've shown previously, LLMs are not always accurate at these tasks. And now we're saying we're going to take those models and use them to assess the accuracy of their own answers and other models' answers. And the prevailing practices of meta-evaluation that are being used, I think, do not guarantee good metric behavior for these LLM judges. And I'll say a bit more about that. So in the rest of this talk, here's the plan. I want to present findings from 2 studies that aim to expose some of the limitations in current evaluation and meta-evaluation practices. And I'm also going to argue for different ways of evaluating and meta-evaluating language models in these settings. So the first half, I'll discuss a study where we conduct, where we try to assess whether models are able to refuse questions that are unanswerable in structured science and biomedical QA settings. Okay, so I argue here that we need to incorporate refusal evaluation directly into LLM evaluation pipelines and benchmarks. And currently we have poor representation of these examples in our data sets. And so for this study, we work with existing data sets to kind of make some of the queries unanswerable and evaluate language models on those queries. And then in the second half, I want to shift gears and talk about, I guess, the complexities of model evaluation and how we might be able to develop better evaluation metrics through stronger meta-evaluation practices. And I suggest one way of doing this at scale with minimal human input through heuristic meta-evaluation. And then, some closing thoughts and discussion. So any pause for a second. Okay. So I'll jump into the first study, which is on evaluating refusal in science and biomedical QA. Okay. So I'll set up the task. So in scientific and biomedical question answering, this task is often framed as being context dependent. So models are given a question and some provided context or context that they're able to retrieve, let's say from the internet or from a trusted database. And then the correct model response, the correct model response or conduct might be to reference that context or the retrieved evidence and use it to answer the question. So, for example, maybe a question like this: do people think rugby headgear prevents concussion? Maybe the model retrieves some context from a paper, Peterson 2002, and then a model generates a response. But in cases where the retrieved context is either incorrect or irrelevant, or maybe consists of it has some internal inconsistencies, then we don't necessarily want the model to generate an answer based on the context or based on its parametric knowledge. Instead, we want the model to express that uncertainty in its output. So from prior work, we know that actually language models struggle with refusal in many settings. If you just ask it a query that's unanswerable, it's very unlikely to refuse to answer. And we also know that pre-trained language models are negatively impacted if they're trained in a kind of context-dependent setting, and we modify or remove that context in some way. So we know that pre-trained language models can be sensitive to irrelevant or missing context in these context-dependent settings. So the goal of this work was to try to understand the interaction here. So how does context and refusal interact in these science QA, these context-dependent science QA settings? Okay, so we set up our experiments to answer 3 questions. How well do language models abstain from answering questions when context is missing or noisy? If we perturb the context, so if we change it, either by making it more noisy or removing it, how does that impact our kind of outcome measures, which is how well does the model perform on the QA task itself, and how well does the model abstain when we expect it to abstain, or when we don't expect it to abstain. And then finally, another interaction here is how does question type also interact with or impact task and abstention performance? So to answer these, we developed this framework with 4 types of context perturbations. Excuse me. So our baseline, here's an illustration of those mean. So our baseline here with the given context, we have data sets consisting of questions with a ground truth context that is labeled by the annotators of that data set, the curators of that data set, which contains an answer to the question. So in the baseline setting, with the given, we give the model a question and the given context, and we just prompt the model to answer the question. Very straightforward, context-dependent QA. Now for perturbing the context, in the no context setting, which is the second option, we simply remove the provided context. So now we're turning a context dependent question task into essentially just a plain question answering task without any context. And then we have the random context setting where we substitute the correct context with a relevant random context sampled from somewhere else in the data set, so completely irrelevant. In these 2 cases, we expect that the model should not be able to answer the question, right? No context is provided. The model is given a context-dependent question. So we expect models to abstain in these 2 settings. And then finally, we also assess this 4th option, which is the noisy context setting, in which we append some random noisy context to the ground truth given context in the data set. So the model still has access to the information that it needs to answer the question, but there's also more noise in that information that's being provided. So in this way, what do we expect? We expect that because the model still has access to the original information, an ideally performing model would still be able to answer these questions similarly to the baseline model. But it's testing kind of robustness to noise. Okay. Yes?
So are these pre-trained models mean that if there is no context, the model is expecting to abstain?
So here we're actually doing zero-shot prompting of the models. They're not pre-trained. And we instruct them to abstain from answering if they cannot answer the question. Yeah, so this is similar to other experimental settings in which people have investigated LLM refusal capabilities, but just with context in addition to just answerable versus unanswerable queries. Yes.
If you use different contexts, you're keeping the same question, you're just either adding context
Or removing it.
but the question remains the same.
Question remains the
And then
same.
you're seeing how that's changing the answer. Is it relevant to also see if I were to take a question and then just rephrase it? Like, same question, just said differently, to see how often it will, like, that kind of perturbation that really is not changing anything. Tells you something about the random variation and sort of the responses. Is that useful for interpreting the, or inferring whether these truly are leading to something real or that's just the baseline noise?
Yeah, that's a great question, and I would say it's related to two things. One is whether models consistently answer the same way to these questions, and we do multiple runs for each question to look at the stability of the responses. But I think the other thing your question relates to is more around so there's like confidence elicitation methods that look at distributions across model responses for the same input instruction and query, and that gives it's a way of eliciting how confident is people use it as a way of eliciting how confident a model is in its answer. So for example, if 8 out of 10 runs result in the same answer, then the model is 80% confident that's the answer versus something else. But maybe that's not.
Well, when you say the same run, what is it? Not, I mean, you're right, so if you put exactly the same prompt, do you expect the same answer, or is there a random seeds in there that actually will produce different answers to the same exact question? Is that what you mean, like running it 10 times, or perturbing the way you pose the question, just using synonyms and so on, just rephrasing, but it's exactly the same question, just phrased differently?
So I think I'm more thinking the first variant, which is you can control some parameters when you prompt these models to sort of like something like temperature, which tells you how whether it's degree sampling or some other kind of sampling across the proper distribution for the output tokens. So you can turn up the temperature, sample across essentially sample a bunch of different outputs, and that's a way of essentially trying to get information about the probability distribution of outputs that the model has generated. But this other point you raised around paraphrasing the question, seeing that's true, we did test some prompt variants, and we know no models are sensitive to prompt wording. But in this case, we're taking prompts as close as possible to the original prompts that were kind of released for testing these particular data sets. And there's just many moving knobs. And in this project, we're saying we're gonna freeze the prompts. We're gonna keep this zero-shot prompts, alter the context provided by models, and see what the impacts are on task performance and extension performance. So that's the scope of this experiment. And I think there's just myriad ways that other knobs can be adjusted. But let me present some of the results and see if it's not going to answer all your questions, but maybe it'll answer some of them. Yeah. Okay. Okay, so we conduct experiments over 4 data sets. Of these 4 data sets, PubMed QA and Bioask contain biomedical questions, and the Casper data set contains computer science questions. So mostly have a range of scientific question answering data sets. Each of these data sets also consists of a different mixture of question types. So 3 of them have unanswerable questions by default. So what does that mean? Unanswerable questions are those that were labeled by annotators as being relevant, but could not be answered using the provided document or context. There are also these Boolean or true-false questions, as well as extractive and abstractive queries. So abstractive queries are kind of free-form generation. We conduct experiments with 6 base models, prompting each model in a zero-shot setting with abstention-aware answer options. So we tell the model, we specify the form of the answer we expect based on the question type, but then we also instruct the model to abstain, or essentially that we use the unanswerable token, so to generate an unanswerable token if the question is unanswerable. And then we evaluate 2 things, as I mentioned before. For task performance, we report either accuracy or F1 based on the specifications of the original data set. And for abstention performance, we report abstention rate. So abstention rate can range from 0 to 100, 100%. So 0 means the model never abstains, and 100 means it abstains in 100% of cases. Okay, so the first thing I'm showing here is just task performance. So the baseline zero-shot task performance of all 6 models on all 4 data sets. And the top row there is the state-of-the-art performance reported in other papers. Right, so those are not our models. But in the zero-shot setting, we actually see that the performance we get for these models and these data sets are actually somewhat competitive with these state-of-the-art model performances. So we're starting from a place where we can kind of compare to what the expected good performance might be on these data sets. Okay, so this is task performance, and now I want to show abstention performance. And the baseline abstention rates actually vary quite a lot by data set and model. So here, everything in parentheses is going to be an abstention rate. We have our 6 models, we have these 4 data sets, and I'm reporting abstention rates in just the baseline setting. So this is with the context given by those data sets, and split out by whether the questions are answerable or unanswerable as specified by the dataset curators. So 3 of these datasets contain unanswerable questions. And what you see here is that, hey, in most cases, models tend to abstain more when a question is labeled unanswerable by dataset curators. This is what we want to see, because we know these questions are unanswerable, so the model should indeed should abstain from answering in those cases. But we also see that's not perfect. Sometimes models do answer these unanswerable questions as well. And then we also see that, for PubMed, seems like actually the answerable and unanswerable questions have similar distributions. So the models are just answering at a similar rate compared to what they do for answerable questions. This is just answerability. Accuracy is on the right side. So now I'm showing results for the no context and random context settings. So recall that in these 2 settings, we're removing all of the information that the model needs, or removing the information that the model needs to answer these questions. Okay. So in the no context setting, there is no context provided. Model should theoretically abstain, although we also know that the real ceiling is not 100% abstention, because some of these questions can probably be answered by model parametric knowledge, but we still see a fairly large drop, which is what we expect. The more surprising thing, or maybe it's not surprising, is that random context is better at facilitating abstention in context-aware settings than no context. So if we just provide models noisy context, they're actually okay, I can't answer this question based on this context, so I'm going to abstain at very high rates. So that's also kind of a positive thing, which is if the information provided is more similar to the shape of the task that the model expects. So like it's a context dependent QA task. So the model should be given a question and context, then it's actually better at refusing. But you can also see that for some of the data sets, for example, Biost, there's just this inability for models to abstain on that task. And that's the only data set that exhibits this inverse pattern of behavior, where the no context setting actually leads to higher abstention. Yeah. And part of that, I believe, is due to the Boolean nature of these Bioast questions and potentially like essentially overfitting to these models have already probably overfit to the Bioast data set. When we look at answer biases for Boolean questions, because we just went and looked a little bit more deeply into these yes, no, true, false questions, and we found some interesting error distributions. Some models exhibited a clear bias for one of the two answers when they should be refusing. So if we took away the context, no context setting, GPT 3.5 and GPT 4.0 had super strong positive answer bias. They essentially always answered yes when they should be abstaining for Boolean questions. In the no context setting, so if no context is provided. Whereas in the random context setting, if we just provide some noisy, irrelevant context, there was this super strong negative answer bias. They would almost always answer no. So there's just, I think casting questions as Boolean questions just leads to a lot of odd behavior because there's been so much, I think they're just kind of overrepresented in pre-training and mid-training data distributions. So beware that we observe lots of kind of odd responses when framing questions as Boolean questions.
In those particular examples, was the quote unquote correct answer yes or no?
It's
Or unrelated?
unanswerable.
Oh,
Yeah.
these are the okay.
Yeah, so
I see.
both of these are
I see.
Yeah, it's in the case where the model should not answer. It always answers in one of these two ways, depending on whether there's a context provided. Yeah. Okay. So, I'm skipping over a lot of results, but these findings, I want to tie them back to the earlier claims that I'm making, which is that models tend to struggle with questions when they should be refusing to answer, because we see a lot of kind of like we just see a lot of kind of unexpected behavior in these cases where the models should be refusing. Actually, I accidentally skipped a slide. Want to also show, here's the task performance in these context perturbation settings. So what we're seeing here is that the context does matter for answering these questions correctly. If we remove the context from any of these data sets, the task performance drops by quite a bit. So that the models do require the context to answer these questions. So this isn't it's not like the models have just simply memorized the answers to all of these questions. We do see this drop in performance. And then we also see some kind of maybe unexpected behaviors around where the task performance increases when we add noise. So how is this possible? And actually, this is possible mostly because noisy context actually greatly facilitates abstention. So if we add noise to the context, models, especially some of the smaller models, tended to abstain more. And because these data sets contain a mixture of answerable and unanswerable questions, we actually see this counterintuitive increase in task performance due to an increased ability to refuse. So what does this imply? It really implies that we shouldn't be measuring refusal and task performance together. Because it's conflating performance on the questions and performance.
So can I ask what the sample size is for these data? So if, for example, if there are like 100 data points in the data set, are you just feeding those 100, all 100 of them, and then you're measuring how many of those 100 the model got correctly? Is that how you're?
Oh, for the task performance?
Yes.
Yeah, so the data sets are all different sizes. So Squad is much larger, it's like several thousand test points, and then PubMed QA and I'll have to look up the exact statistics. But PubMed QA, Biost, and Casper are in the hundreds of samples in the test split. And yeah, for task performance, that is exactly how it's assessed. So we have ground truth answers. We prompt the model to generate answers, and then we just compute accuracy or F1. Yeah.
So no replication there, but no.
Oh, like no error bounds? Yeah, no error bounds on this table. But I also think that the like what I'm mostly trying to communicate is that these deltas are quite large, and that sometimes adding noise actually, like adding noise leads to this counterintuitive result sometimes, because there's actually two moving things. One is whether the model is answering the question correctly and whether the model is refusing correctly. And we shouldn't be combining those two numbers together, because now we can't disentangle whether this increase is actually coming from the model answering more questions correctly or refusing to answer more queries correctly. And those are really different qualities, model qualities. Okay, so okay, so I now want to shift gears and talk about meta evaluation, but I don't know if folks have questions about. Okay, so now I want to switch gears. This part of the talk is very different. So I want to talk about strategies for developing better evaluation metrics in these generative settings. So the first thing I'll mention here is that evaluation for long form or free form generation tasks, they tend to go beyond accuracy or correctness. So not only does the answer have to be correct, whatever the model produces might also need to satisfy other requirements depending on the how the task is defined. For example, whether the model is generating fluent or coherent text, whether that text is faithful to source documents, if there are source documents provided. If the answer contains citations, are they appropriate or correct? Is the answer on topic, and so on and so forth. So there's lots of these types of criteria that these answers might need to fulfill depending on what task we're studying. And indeed, we see a huge diversity of evaluation criteria being assessed across NLP tasks based on the definitions of those tasks. So this set of histograms, this comes from our survey of evaluation in NLP papers. And we're showing the top criteria that are evaluated for different families of NLP tasks. So for example, in dialogue and interactive systems, or papers studying dialogue and interactive systems, the most commonly assessed evaluation facets are things like relevance, coherence, fluency, followed by accuracy, informativeness, consistency, helpfulness, and so on. These are stemmed. So I'm showing this plot mostly to indicate how much diversity there is in the types of qualities that people are care about in these textual responses. But also I want to emphasize the difficulty of these criteria. So like, what does what does informativeness mean and how it's operationalized can differ a lot across papers. There's just no consistent definition of that. And I also hope that it's fairly obvious from the names of these criteria that none of these dimensions can be very easily captured by any kind of deterministic automated evaluation. Right. So these are just hard things to evaluate. But now I want to talk about how to evaluate. So yes, we want a good evaluation metric that can capture those types of criteria that I showed on the last slide. So what does a good evaluation metric mean? Well, I think this is probably more familiar to all of you, but a good evaluation metric should be sensitive and specific to the measured criteria, right? If we have a good response on that criteria, then we want our metric to score that high. If we have a better response, we want the metric to score it higher. If we have a bad response, we want it to score it lower, right? And so I would say this is a prerequisite to having a good evaluation criteria. There are plenty of other properties that are desirable, but just thinking about these. So what makes this hard to achieve? So this is how I think of the problem, like in a very simplistic sense. On the x-axis, we have the range of all possible outputs, spanning from those that do not meet our criteria of interest at all to those that maybe perfectly meet our criteria. And then on the y-axis, we have some metric that we're going to compute to evaluate this criteria. And a good metric, one that is sensitive and specific to this criteria of interest, should have some sort of monotonic response curve, where if the output is better along this criteria, it scores very highly on the metric. And if it's poor, then it scores poorly on this metric, right? Now, for any metric that we're evaluating, we need to estimate the shape of this. So now I'm talking about meta-evaluation. How do we know that the metric is in fact responsive to our criteria? We need to estimate the shape of this metric response curve. And the problem is, usually, maybe we only have one gold labeled data point in our data sets that says this is a reference answer that maybe perfectly meets our criteria. And we're already kind of using that as a proxy for what it means to perfectly meet our criteria. But we can place it on the upper end of this curve. And then maybe in some cases, we're able to bootstrap extremely poor examples that don't meet the criteria at all, maybe through random sampling or other kinds of negative sampling. But regardless, I think the vision I'm trying to, or the image I'm trying to paint here is that we don't actually have anything in the middle, or like rarely do we have anything in the middle with human labels that's going to help us estimate the shape of the metric curve. Okay, so it's really difficult to estimate the shape of this curve. What we really need to properly estimate the shape of the curve is we need many answers across ideally this full spectrum of the entire range along this kind of criteria dimension. And we also need to know or be able to estimate their relative locations along this x-axis. And then if we have this information, then we have our metric of interest that we're trying to characterize. And then we look at the metric values, and maybe the metric gives us these green dot values, and we can say that actually this is a fairly well-calibrated metric. It is well correlated with our criteria of interest. Versus something like this, where if these red dots were the values produced by our metric, then this is a very poorly calibrated metric that is poorly correlated with our criteria of interest. So all this is still pretty hard because we don't actually have the diversity of points down here or their relative locations. And in practice, we try to estimate or like produce some of those points through some amount of human judgment. So we might take a bunch of models, produce a bunch of responses, put them in front of a set of human judges, maybe do pairwise comparison, and that gives us some kind of ranking of these answers along the criteria spectrum that we care about. Okay. And then we go back to our metric space. Maybe it's LLM judges, maybe it's an automated metric. We report correlation with these limited human judgments. And then we, if the correlation is high, maybe we say the metric is good, and we can generalize and use that metric to evaluate whatever task we're interested in at scale, right? And at scale in a way that we can't do with human judgments. And the current practices, I would say, generally they do lead to these system level correlations. So if we collect, let's say, 200 human judgments, we do correlation with LLM judges, and we get maybe reasonable system level correlation. And what I mean by that is maybe the metric places let's say here we're evaluating 5 different models, 5 different systems, and the metric, the LLM judge metric or the automated metric places those systems in a similar order to what the human judges rated. But at the instance level, we very, very rarely see good correlation. Actually, we often see pretty poor correlation. So this is just some references to prior work that has shown this in news summarization with automated metrics. And this is kind of recent work that I'm involved in, where we looked at deep research systems, and we've really found quite weak instance level correlation for the LLM judge and rubric. They're actually rubric-based judges that people are using to evaluate deep research systems. And this plot I'm showing comes from this Deutsch et al. Paper. And I think it kind of illustrates maybe what's going on. So in these 2 plots, the left side is the kind of system level score distributions for 5 different systems provided by humans. Right side is the same system, same distributions for those systems produced by a metric. And in this case, we actually don't even really see system level correlation, right? The human thinks that system D is best, followed by A, followed by E, followed by C, followed by B, if we're looking at medians. And on the metric side, we get this relationship. But either way, what we're seeing is that the within system variability here for scoring is as high or possibly even higher than the between system variability at the instance level. So if that's the case, then we really can't use human judgments as a great estimate of criteria compliance. So maybe what's happening, if we go back to here, is we're actually not getting sufficient diversity over the criteria spectrum that we care about, and potentially the error bars around the criteria estimates that are produced through human judgments are actually very large compared to the distance between answers. Okay, so try to propose some solution. So in response to these limitations of collecting human judgments, we propose a heuristic meta-evaluation strategy to better approximate the shape of these metric curves. And as part of this strategy, we're trying to synthetically produce more diverse outputs over a set of criteria of interest. And then we're going to use that synthetic data to estimate the shape of the metric response curves. So in this work, we use the task of plain language summarization as our case study. So PLS is the task of taking a complex piece of text, for example, scientific text, and rewriting it so that it is more approachable for a lay audience. And it's a good task to study because a good model output actually has to satisfy a range of criteria. So the text needs to be coherent. It needs to be informative and provide additional background knowledge to help people make sense of the text. It has to be factually accurate, and the text has to be simple and more comprehensible. And I know I'm running out of time, so maybe, okay, I'll just quickly try to wrap up. So we define a set of controlled perturbations along each of these criteria that we can control. So for example, maybe we take the original text and we introduce factual errors by substituting in different entities. Or maybe we increase the simplicity of the text by substituting parts of that text with more simplified text. So these are perturbations that we can apply to different portions of the text in a controlled way. And we defined 11 perturbations corresponding to the criteria from the previous slide that's important for plain language summarization. And we are able to apply them to the ground truth summaries from existing benchmark data sets and go kind of across the range of perturbations. So either perturbing none of the text to a little bit of the text at a time to introduce more and more factual errors, or delete more and more information, or add more and more simplified text, and so on. And so in this way, we are kind of creating this controlled test bed in which we can then evaluate metric behavior. Okay, so we do that for automated metrics, for model-based metrics, and for LLM judges. And I'll just show the results for LLM judges. So we meta-evaluated the different LLM judges along each of the perturbations that we introduce. So here we're using GPT-4o, I believe, as the judge model. And we're prompting the model to score each of the summaries on each of these 4 criteria. And we have, many, like hundreds of, like many thousands of instances, because our benchmark includes many hundreds of instances, and now we have perturbed variants of those instances. And what we can see here is that for some perturbations, the LLM judge does in fact respond exactly how we would expect it to perform. So for example, this mustard colored line is negation. So we introduce more and more negation as the perturbed percentage increases. And we do in fact see that faithfulness goes down. That's what we want to see, right? Because we've negated a bunch of sentences. However, that's not always consistent, right? So if we look at another one of these, like for example, like maybe something like the antonym swap, or the number swaps, which also introduce factual errors. Those are there's definitely a decline in the rated faithfulness, but it's much the model is much less sensitive to those on average. Okay, this is average over many instances. I'm not showing error bounds on this plot because it would just be kind of overwhelming. But I will say that we haven't exactly addressed the instance level variability problem. The instance level variability remains extremely high, and we don't have good metrics or judge models. I would say there's no task where I believe LLM judges are suitable for instance level judging right now. Yeah. Okay, so I'll end there. I think effective evaluation is really critical in these spaces, especially as language models are being deployed and integrated into a lot more systems that are serving scientific or clinical uses. What I'm making the case for is that in evaluation, we need to improve how we measure model performance in cases of low knowledge confidence, right? These cases are difficult for models. Models tend to perform less well in them, and they're not well represented in existing benchmarks. So we're usually not measuring. And then on the meta evaluation side, this lack of effective evaluation metrics really stops us from iterating on the kind of first 2 points here. So we need more effective strategies for characterizing the performance of evaluation metrics and LLM judges so that we know kind of what to expect if we're using them to assess our models, our systems. And then this problem is continuing to increase in complexity, right? With agentic settings, with pipeline systems, right? There's multiple independent components that we need to evaluate. How does retrieval work relative to refusal and how do we evaluate that? What about query refinement, refusal follow-up, and so on? So there's a lot of work needed to generalize evaluation, meta-evaluation to those settings. Okay. I'm done.
Thank you so much. Are there any questions or people on Zoom have questions? Or I can ask one too. No, but yeah.
Yeah, thank you. This was interesting. I have I guess, a general question, which is. Like, what exactly, or who exactly would you say is the target audience for this work? Like, are you working with the companies that are producing these LLMs and trying to help them do things better, or are you more working from a different perspective?
Yeah, I would say it's essentially the entire NLP research community. So how do we construct benchmarks and why? Do we include certain instances and not other ones? When we're reporting that we're using LLM judges as the primary evaluator, how much confidence, like one should also report how much confidence we have in that evaluator. And then I would say kind of beyond that, these models are also being integrated into a lot of user-facing systems. And I actually think that those are the right places to also integrate this kind of evaluation. Because what we found is like, if you just ask a researcher, like what's a hard question that models should not be able to answer, that's a hard question to answer. It's hard to think about like what's difficult. But in practice, and for many of the tasks that we've built systems to support, there's naturally occurring uncertainty. And all I'm saying is that we should be looking into those natural sources of uncertainty and making sure that we are considering them when evaluating for whatever end use case. Yeah.
Maybe I'll ask a quick one. For these different metrics, is it, I don't know how to ask this question. Is it well agreed upon how these metrics work? Like
the LLM judges?
two researchers argue over how coherent this is. And so if two researchers are already arguing and we're the labelers, then shouldn't I naturally expect the LLM system to also not really be able to assess how coherent it is? Like something about, I guess, the human variability part, because we're using the human variability to, make a judgment about how good the AI systems are, or, curious about, yeah.
Yeah. I don't want to say anything systematic, right? Like that systematically applies across all these criteria, but I do think from a lot of mostly experience designing these annotation tasks, that if you're asking, like if you give humans a set of annotation tasks and humans tend to disagree on like what the rating should be for a particular criteria, those criteria also tend to be harder for the LLM judges to evaluate consistently. However, it's unclear to me whether that comes from like the task is just less well defined. So usually, we give the same instructions for evaluation to both humans and LLM judges. So if the task if you could define the annotation task better such that humans agree more, maybe LLM judges would also agree more. But it's unclear whether the variability comes from the task definition or the actual construct that is being evaluated. And I'll say, like in a recent evaluation study we did, we evaluated consumer health questions along correctness and whether they adequately address safety information. And we found that experts had really high agreement on correctness of information, but really poor agreement on whether enough safety information was communicated in the answer. And models similarly had problems in the same direction. So maybe it like, but I don't know where that where to attribute that variability. Okay.
All right, well, let's give Lucy one more round of applause. Quick announcement. So next week we have our Great Apprentice lecture. We will actually not be in this room. We'll be in Faggy and Genome Science. And then the following week, our very own Marco will be giving a seminar for the PhD visits, and there'll be a different room that'll be on the first floor of A. So anyways, so we're moving all around. I'll email it out so we all know where to go. But anyways, good to see you all, and welcome to you. I don't know. So our for these metrics, the vision how it works is we almost learn how the metric is defined as we give like for safety. I don't know how safety is defined, but how I'm going to define safety is how my experts define safety, and whatever that is, I don't really know how to define it myself. That's what I'm trying. Is that how we come up with a lot of these metrics?
Working with end users to, I'd say it goes in both directions. One is if there's theoretically motivated criteria, like the task should satisfy, then those need to be measured. But then oftentimes we're measuring user-derived concepts. And that's why there's so much variability across these tasks. Yeah, so.
You guys.
I just got a question about how you emphasize the confidence score versus general model. Is it something like the decoding confidence score, or is it something that LLM generally?
There's many confidence elicitation methods. If you have access to the model internals, then you can compute things like probability distributions over outputs. But if you don't, if you can only sort of prompt, then there's lots of methods for eliciting verbalized confidence. Some of those that might be sampling. I think I was talking earlier about like sampling a lot of responses and seeing what the distribution is. There's also just directly, the vanilla prompting, like you just ask the model for verbalized confidence. But almost all of these techniques result in like models are not very calibrated for confidence. They tend to be overconfident and poorly calibrated. So it's like the confidence estimates are if you don't calibrate, they're almost always in the 80s. Like if you ask for a confidence score in the range of 0 to 100, they're almost always at the 80 to 85s, even if the accuracy of the model in the task is something like 20%. So they're just very poorly calibrated. If you just
Well, the reason I asked is I did the data extraction from the literature I explained to you before. So I will basically to let the LLM language model to generate how confidence score.
That confidence score is not very good. I guarantee it. One way you can improve it is we have a paper on that introduces something called answer-free confidence elicitation. So if you actually ask the model to generate a confidence score without answering, it is much better at confidence estimation than it is if you ask it to answer and estimate its confidence. It's because it's like a distribution machine, right? Like it's already spat out the answer. So if you ask for confidence, that confidence is going to be correlated with the answer. Whereas if you independently query for it, it is significantly better. Yeah.
That's interesting. Well, I guess there have a many way to generate a confidence interval. I mean, confidence score, including confidence interval.
Yeah, there's like there's a whole survey on different methods for confidence elicitation, but all of them, even the best confidence calibration methods, LLMs in particular tend to overestimate their confidence relative to past performance. But independently, answer-free confidence estimation, it works.
Oh, thank you for your talks.
I've done a little bit of research with LLMs on medical setting, poetry. And I was kind of thinking like, did you have any like resources as checks of articles you mentioned here, but did you have any resources on just like kind of looking at LLMs in more medical settings as far as some of that research or?
I mean, there's a lot. Is there-
I have, yeah, so I have, like, I think that essentially assessing like some of the responses is definitely, that's an area that I'm interested in. Because that's kind of similar to, from my previous research in poetry, I was essentially looking at its generation, its poetry generation, like can it fit forms, can it be grammatically accurate and things like that. So like applying that to a medical setting as a biostatistician, like reading more on topics like that definitely be interesting.
Yeah, so there's just there's a ton. I'm just trying to throw something out there that might be useful. I mean, I think in a lot of so it depends on what kinds of generation tasks you're doing. I think there's been a lot more development in these maybe health or science related deep research systems, so we might look into the evaluation that's being used in those cases, which are mostly rubric driven, and maybe that would apply in something like poetry setting where you have, form content based criteria. So maybe looking at something like just like health bench to start and seeing how they use that. There's also the SQA eval paper that I think does a pretty good job laying out the different problems in the space. It's a little more science and a little less directly health, but that's the be so.
Yeah, thank you.
Great.
All right.